say, kick off our first webinar of 2016, which is a real sort of an important year for Open PHACTS. And I thought what we'd do to start with is just give you a brief introduction to where Open PHACTS is today, and just to give you that introduction and to put it into context, and then move over to some of the sort of the more detailed work that's been going on the patent analysis parts of Open PHACTS too. So for those of you that don't know too much about Open PHACTS' original mission and where we are now, the role of Open PHACTS was as a IMI project that started in 2010. And its role was to integrate a wide variety of biomedical data and information to allow it to be accessible under a single API, and to build services on top of that to support drug discovery questions. And it started off in 2010 and then had a 2-year extension to the point when it's now come to a close in 2016. And it's now operating as a sustainable foundation. So the work today that we're presenting is both work that was done as part of the original IMI project, as well as work that's been funded now as part of our foundation status, which is paid for by our membership. And as I say, we're keen to showcase what's been happening in Open PHACTS and also what will be happening in the future. So we certainly welcome your comments today on things that we could be doing, different things, and we will be covering some of those other topics in future webinars, you know, probably every month for the next period, and we've already got some webinars lined up for the spring and early summer. But welcome contributions from you as well if you have a particular interest in presenting in this area. So again, just to help you sort of put Open PHACTS into context compared to probably all the other data sources that you're using as part of drug discovery research, the role of it was to bring a wide but high quality set of data sources together to ask, to support a number of key business questions that researchers needed to ask across data sources, and to be able to access that data easily, to access a sort of a consistent set of data that is bringing together a range of different information, whether it be bioactivity data from SureChEMBL, whether it be ontology data from Go, whether it be protein data from UniProt, etc. And bringing in also other more emerging data sources like DisGenet, which covers the linkage between disease and gene. And what this talk is about in a minute, about the work that's been going on in 2015 around extending or bringing in SureChEMBL into Open PHACTS, as well as some of the work that's been funded by the project and by Open PHACTS to bring in the bioannotations, which I know that George in a minute will talk about. So it's been a project which has had a large number of contributors and contributions to, and many of the data source providers listed here have been instrumental in helping bring that data together in a way that it can then be exposed within the Open PHACTS environment under a RESTful API, which is available to you, as well as other ways that as members you can also contribute to Open PHACTS. And just this slide just gives you a little bit of an update on the evolution of Open PHACTS from the left-hand side, in that the first goal was to deliver an interoperable set of public data from those data sources which were listed before. And we've actually added in a number of things as part of the project over this last period. So one thing that was done early on was also the ability to merge in commercial data. So we've done some pilots with a range of commercial data providers such as GVK Bio and Thomson Reuters that allows you to merge in not just the public data but available commercial data that fits the data model of Open PHACTS. And more recently, we've developed a virtual machine version of Open PHACTS that runs on Docker or deployed through Docker. And that would then allow you to deploy Open PHACTS in your own organization, for instance, and that would be particularly relevant to the right-hand side here, where you might wish to bring in private data and merge that with the existing data set to be able to ask questions across both public and private data. And that's currently being deployed or being used in a couple of pharma situations at the moment. And we've also had, because we have a cloud-based API, we've been able to have that sort of security audited and hosted such that it passes the needs and requirements of commercial users. So the project has evolved quite a bit from its original sort of goals, and we hope that these extensions will continue under the guise of the foundation model as well. The other key part of the work, as I mentioned, that is focused on the API access, is that we've been able to work with a number of ecosystem partners, namely those that are specialist in the sort of workflow tools, for instance, KNIME and the pipeline pilot tools from Biovia, as well as working with other sort of high quality analytics tools, and we are beginning to build up a relationship with the Data Warrior tool that some of you may already be aware of, as well as having created a host of other e-apps, either as part of the project, such as SureChEMBL Navigator, or ones which people have linked in themselves to use the data sources or the API and the data access that Open PHACTS provides. And we're certainly always keen to talk to people about how working with you more to get your application using the data that's within Open PHACTS and working with the community, the science community that we have at the moment as well amongst our members. So this is an extension of the API to service a range of different systems in the future and build up an ecosystem. And we certainly expect the work that we'll talk about in a minute with the patent work to expand this type of usage too. I've already made mention of the role of the foundation, and just a bit of a heads up, and you're welcome to contact us later as well about interest in this, is that the foundation is a registered charity, and it's funded by membership, and we currently have a range of pharma members at the moment, as well as some academic partners, and the role of it is to ensure that Open PHACTS is sustainable and can grow and offer relevant extensions based on what the membership want to do next. So part of the belonging to Open PHACTS means that you can participate in discussions on what functionality is added in the future, as well as prioritization and equally early access and privileged access to certain parts of the project that are now going to be delivered in the future. So as I say, please get in contact if you have any questions on membership, and we'd be delighted to help you out with that. Just as I said, the project involved a wide range of participants, and this just lists lists them here. And as you can see, it covers a broad breadth and experience of drug discovery. And we hope that this has enabled us to represent the key questions that our users might want to ask, and we certainly want to bring in others and other partners going forward. And as it says here, you can contact us through Twitter and through email, and we have a regular newsletter that will update you on things coming out in the future. So without delaying any further, I would like to welcome and thank George Papadatos from the EBI-EMBL group, who he works in the SureChEMBL group at the moment, and he gave this talk at a successful meeting that we had in Vienna a couple of weeks ago, and it was so well received that we thought it was really worthwhile giving it out, being able to introduce it to others who weren't in Vienna. And so George will take us through the patent annotations from SureChEMBL to Open PHACTS, And I'll hand over to George now and welcome him to the webinar. So just handing over control back to George. So
yes. So give me 1 second. Yes. Okay, I hope you can all see my slides and hear my voice. Thanks, Nick, for the introduction, and welcome everyone to the webinar. My name is George. I work at the SureChEMBL group at the European Bioinformatics Institute, just south of Cambridge in the UK. So today I would like to talk to you about 3 things. The first one is a quick overview of our SureChEMBL pattern resource in terms of its pipeline, content, and user interface. And then I will focus on the work that we did for Open PHACTS, which involved the extraction of chemistry and biological entities from the full text of patent documents, and then subsequent integration with the Open PHACTS platform. And then I will finish with some use cases and examples of how you could interact with the data that we provided to the Open PHACTS API, and how you could use the API to come up with hopefully useful examples. So as I mentioned in the beginning, I work for the SureChEMBL group, and of course the group is mostly known for the SureChEMBL database. So what we do in SureChEMBL, we extract scientific facts from the primary medicinal chemistry and chemical biology scientific literature. So these are bioactivity measurements that connect and link small molecules to biological targets, from single proteins to protein families, cell lines, and organisms. And then we spend a lot of time organizing the data, integrating, curating, standardizing, normalizing the data, and in brief, adding value to the data, and then we provide the data back to the community. So we've been doing this for a long time, I think for 7 years now, and people have been asking us all the time if we were going to do something similar for patent documents in addition to the scientific literature. And this is, of course, very important because, as you know, people file and apply and search for patents because they have legal, financial, or commercial incentives. And although patent documents are public documents, they have been traditionally linked with secrecy and obfuscation. And the field of patent searching and patent annotation has been traditionally closed and very, very commercial and very expensive to use, which made this very important source of information inaccessible for academics and SMEs, for example. And that's a huge shame, because patents represent an unprecedented wealth of knowledge. So there is a lot of knowledge hidden and locked within the text and the images of patent documents, and most of this knowledge will never be disclosed anywhere else in any other source of information, such as journals or books, for example. And even if it does appear, there is on average a substantial lag, a time lag between the disclosure of some information in the patent literature and the disclosure of the same information in the scientific literature. And this ranges. So when it comes to compounds, this is 2 years. When it comes to approved drugs, there is a 4-year lag. And then when it comes to biological targets, this is even longer. So the average lag is 4 to 5 years. So the situation with patent documents and patent searching was improved a couple of years ago when SureChem was donated to the EMBL-EBI, and then it was rebranded and converted to SureChEMBL. So what SureChEMBL does This is the slide that summarizes what SureChEMBL does. It's a pipeline, it's an automated pipeline which starts with the full text of the patent documents as submitted by the four main patent authorities of the world. That's the WO, the EPO, the USPTO, and the Japanese patent authority, the JPO. So the data is aggregated, and then there is the automated entity recognition software which will scan the full text of the patent document, and it will try to identify chemical entities in the text. And then we use 5 different name to structure tools that will try to convert these chemical entities to the corresponding chemical structures, which will then be stored in a database. At the same time, there is another branch in the pipeline which does the same thing for images. Images of 2D compound structures, which are, of course, usually depicted in patent documents. Again, we use a tool that will try to find these images, convert them to the corresponding structures, and again, these will be stored into the database. And the database is exposed to the public via a user interface. And I have to say here that this whole pipeline is hosted in the cloud, in the AWS. It's fully dynamic. There's no manual interaction or manual intervention, and every day, and it's live. So every day, new patents will arrive to the beginning of the pipeline, and again, the pipeline will go on. It will try to find the chemical entities, convert them to structures, store them to the database, so that this information is accessible via the interface. And this is how the interface looks like if you go to SureChEMBL.org. So, for example, you can start querying this database. You can write your own keyword-based queries, which can be simple or it can be sophisticated and granular enough. So you can use Boolean operators, brackets, wildcards, and then what is more important is that you can combine these keyword-based searches with, chemical queries. So you can sketch a substructure and do a substructure search and combine this search with your keyword-based search. And then you can browse through the full text of a patent document, and you can see in light blue all the chemical entities that were identified in the text or the images here with light blue color. And of course, you can click on any of these entities, and you can see the corresponding structure. So this is what the SureChEMBL pipeline and user interface does. And of course, after that, you can export the chemistry that was found within a patent document, and you can subject your export to physicochemical property ranges in order to remove trivial compounds or noise and only download what is relevant and what is important to you. And this will be downloaded in the form of a comma-separated file. And then when it comes to data content for SureChEMBL, it contains about 17 million unique structures at the moment that come from more than 14 million annotated patents, and of them 4.5 million are life sciences relevant. And as I said, this is a dynamic process, and the rate of growth is really, really impressive, I would say. So there are 80,000 novel compounds that are extracted from more than 50,000 new patents every month. And because this is a fully automated pipeline, and it doesn't require any manual intervention or interaction, the turnaround time is also very quick. So it takes just a couple of days for a patent to be published by the patent authority, to the point that this patent is chemically annotated and searchable within the SureChEMBL system. Right, so that was the overview of the SureChEMBL pipeline and the SureChEMBL resource, but what we did more recently is that we extended the pipeline and we complemented the pipeline with biological annotation in addition to the chemical one. So we added another component here that does the biological annotation of the full text of patent documents. And this slide provides more details on how this was done. So we used a commercial tool called Termite, which is provided by SciByte. So Termite is a biological entity recognition software, and we used 4 million life science relevant patents from SureChEMBL, and we ran Termite against it. So Termite flagged and identified gene names and then mapped them to Hugo symbols and also diseases and mapped them to MES IDs. And of course, Termite also annotates the exact section where these entities were found. So there could be in the title, abstract, claims, and description. And the other thing that we did is that we gave every entity a relevance score, an integer which ranges from 0 to 3. And this is because in patents, the inventors and the authors will trivially mention tens or hundreds of protein names and gene names and compounds in order perhaps to obfuscate. So we use some algorithms, some text mining algorithms to try and derive relevance score so that you can use the score in order to remove the noise and focus on what is perceived to be the most important entities. So this is how we did that. For genes and diseases, we used the different clues in the text. For example, if an entity occurs many times, or if it occurs in the title or in the caption of a figure or in the header of a table, this is more important than other terms. So this is our scoring scheme that ranges from 0 to 3, 3 being the most important entities in the patent. And we'll see later on in the talk how you can use this score to filter out the noise and keep only the relevant entities. Again, we did the same thing for compounds. Here the main assumption is that the compounds that are important and relevant to the patent will have a busy chemical space around them, and they will have a larger number of close analogs among the compounds found in the same patent and the same patent family. So again, we used a similar scoring system from 0, which are compounds that are very trivial, or solvents, reagents, substituents, and things that are not relevant to the patent, to 3, which are the compounds that have the greatest number of nearest neighbors within the patent, and these are likely to be the most important compounds in the patent. So to summarize what we did, our work for Open PHACTS, we started with 4 million full-text patent documents, and we annotated them, and we found and identified and mapped both the chemical entities and also the biological entities. The patents follow are mapped to using the SureChEMBL identifier. So you have the code of the patent authority followed by a number followed by the kind code, and we also provide bibliographic information for these patents, i.e. title, date, and classification codes. The compounds are mapped to their unique SureChEMBL ID. The genes, as I mentioned earlier, are mapped to the Hugo symbols, and diseases are mapped to MES terms. And again, these are also annotated with a relevant score from 0 to 3. So this is what we did for Open PHACTS, but also there are some things that they're out of scope for this work. For example, there is no Marcus extraction. This is something that people ask us frequently. So SureChEMBL will only identify and extract exact compounds and not generic or families of compounds. The other thing is that what we did is a bag of words approach in text mining, not a natural languages processing approach. So we didn't use, for example, verbs or certain trigger phrases to link compound X with target Y. We also didn't do extraction of bioactivities. This is what SureChEMBL does manually. And at the moment there is no chemistry search, so you cannot go and do a similarity or substructure search against the pool of the SureChEMBL compounds via the Open PHACTS API. And finally, the coverage of patents stops in April 2015. Although SureChEMBL is dynamic and everything in SureChEMBL is up to date, the subset that we used for the Open PHACTS work at the moment stops in April 2015, but there are discussions ongoing to provide a mechanism for incremental updates. So this is a screenshot of the Open PHACTS patent API. This is a list of all the relevant calls and methods of the API that allow you to fetch information from patents. This is still in development, so you will not be available to access this just yet. And what you can do with this API is you can start from a patent document and you can fetch and extract all the information about the patent, about the compounds that are found in this patent, or the diseases, or the targets. And of course, this also works in reverse. So you can start with a compound and you can find all the patents where this compound is mentioned. And you can do the same for targets and diseases. But what is perhaps more important is that you can, once you do that, you can start inferring links among these three entities and types. So for example, you can say, you can start with a compound and then you can fetch all the targets for all the patents, sorry, for this compound, and then from these patents you can fetch all the targets, and then you can create links between this compound and the targets that you find. And this is what I'm going to do. I've got two use cases or examples here, and I'm going to illustrate how you could use the Open PHACTS Patent API and how you could derive your own links between these three different entity types, the compound, the diseases, and the targets, via their co-occurrence in patent documents. So this is the first example. So I will start with a patent document, and I will get the compounds, the genes, and the diseases mentioned in this document, and then I will use the relevance score and the frequency to filter out the noise and keep only the important entities and see if these entities make any sense. So this is the patent that I will use. It is a patent that was published in 2010 by GSK, and you can see the title and the patent ID. It's a US patent, a granted patent as well. So I will use 9 to illustrate the Open PHACTS API, but as Nick mentioned, you can also use components for Pipeline Pilot. So I can start with the patent URI and provide this to the API call to get all the entities for this particular patent. And this will return 586 entities, which are listed in this 9 table. So there are entities, there are molecules, there are diseases, and gene entities in this table. And you also get, for each one of them, the relevance score from 0 to 3, as I said, their frequency in this particular patent, and a Boolean which tells you which section in this in the patent these entities were extracted from. Okay, so I've got my entities from this particular patent. So let's look at the target and disease entities. So there are 178 of them, and then you can use the relevance score to keep only these with a value of 2 and 3. And if you do this, 23 remain, and then you can visualize the remaining ones in a tag cloud, and the size of the tag cloud will be sorted by frequency. So the larger terms will have a higher frequency in this patent. So this is how it looks like. So in purple color, there is the gene that was found. It's only one gene that was found in this patent. And then in the orange color, there are the diseases that were found, the most frequent and most relevant diseases that were found in this patent document. Okay, but so now let's check whether what we find by means of text mining using the Open PHACTS API and using the annotations that we provided from SureChEMBL, let's see if these make sense. So in order to do that, we can use the actual patent and check the abstract of the patent to find what are the relevant diseases and relevant genes and biological targets for this particular patent. So if we look at the abstract of this patent, so you will see that this is an invention that relates to novel derivatives of a particular compound family which modulate the P2X7 receptor. And this is exactly what NIME and the tag cloud are patent. And again, if we carry on reading, we'll see that the P2X7 receptor mediates disorders such as pain, inflammation, and neurodegeneration. And again, if you check the tag cloud, you have pain, inflammation, neuralgia, and neurodegenerative disease and neuropathic pain, which are all synonyms of inflammation, pain, and neurodegeneration. So you will see that what we read in the patent is very close to what the text mining tells us about this patent. Okay, so let's move on to the compounds from this patent. So we have 408 compounds that are extracted and found in this patent document. And again, you can use relevance score to remove irrelevant ones. And then you have 201 remaining, and you can of course visualize them using NIME. And of course, the chemists among you will see quickly that there is a pattern and a trend when it comes to the scaffolds of these compounds. And if you use the RDKit MCS node to do a maximum common substructure in these 201 compounds, you will see that this is how the scaffold of the maximum common substructure scaffold of these compounds look like. And of course, you can compare this with the actual Marcus that is reported in the patent document and see if it makes sense. And if you do that, you will see that, yeah, exactly, what we have from the MCS is spot on. So without knowing anything about the Marcus structure, we will see that we can approximate the Marcus using the maximum common substructure of the compounds, of the relevant compounds that SureChEMBL extracts from this patent document. Okay, so that was the first quick example and use case. So let's see now another one whereby we will start with a compound, in this case an approved drug, and we will search for patents for this compound. And then we will also try to get disease and target entities from the patents that we find and see if we can derive any links effectively between the compound that we start with the targets and diseases that we found co-occurring in the same patent documents. So we'll start with a compound, a drug, which was approved in 2005, so very recent. It's called eluxadolin or Viberzi by Johnson & Johnson. So again, I'm using NIME to do all the work with the API. So first of all, I have only the structure. So what I can do is I can use UniChem. UniChem is a service provided by the EBI. It's our universal compound resolver. So this UniChem, what it will do, it will match the structure to database ID, in this case SureChEMBL. So the ID for this particular structure of Viberzi is SureChEMBL 12971682. So once I have this compound ID, I can form the URI and I can provide it to the API, and in particular this call, the patent by compound call, and I can get back all the patents that mention or contain this particular compound. So I find 17 patents, and this is what I call the patent tome for this particular compound, for eluxadolin. And this is the list of the patents, and this is sorted by chronologically. So the earlier patents are at the top, and you will see from the title that eluxadoline appears in patents in composition of matter patents, as we call them. So, for example, the novel compounds as opioid receptor modulators, but also eluxadoline appears in patents that are related to formulation or process chemistry. For example, there is the third one called process for the preparation of opioid modulators, and there's another one called novel crystals and process of making 5-methyl-2-methoxy, blah, blah, blah. So what I want is I want to use the information that I can find in the API that relates to patent classification codes and effectively keep only the novel composition of matter patents as opposed to process or formulation patents. So for that, I'm going to use the API call for patents, and then this will provide me with the classification codes, and I can use some particular values, for example, A61 and C07, and filter down my set of 17 patents to only 11. And for these 11, I can again fetch all the entities and use a relevance score and frequency to filter out the noise and keep only the important entities. And in the end, I will end up with 2 targets that come from these 11 patents and 21 diseases. And again, I will try to visualize these entities with tag clouds based on their frequency. So these are the relevant targets from these 11 patents for eluxadoline, 2 opioid receptors, delta and mu, respectively, and a number of diseases such as pain, constipation, diarrhea, gastrointestinal diseases, etc. So let's see. So these are the targets and diseases that are related to eluxadoline according to their occurrence in patents. So let's see if this actually makes sense. So this is the FDA prescribing information for Viberzi or eluxadoline. It provides information about its indications and use. So you will see very quickly that it is indeed a mu-opioid receptor agonist, and it's used for the treatment of irritable bowel syndrome and diarrhea. And this is exactly what we've got from mining patents using SureChEMBL and Open PHACTS. SureChEMBL and Open PHACTS don't know anything about the prescribing information, and yet what the findings are confirmed by the FDA prescribing information. So I guess the take-home message in this webinar, in this talk, and I'm reaching to the end of my presentation, is that it is possible now to go and use the API and automatically extract and link the key structures and scaffolds, targets, and diseases that occur in medicinal chemistry, in the medicinal chemistry patent corpus. We're using only a high-throughput text mining approach, no NLP, and we use simple heuristics to get an assessment of the relevance of the terms, of the compounds, and the gene and the diseases. So it's possible to link these 3 entity types together automatically. So other things that you could do, for example, you could add this information, you could add the calls to the Open PHACTS API with your own workflows and pipelines. So for example, you could have drugability or target validation use cases whereby you start with the target, you find all the patents, from these patents you get all the relevant diseases, and you try to find links between targets and diseases, for example. Or with a target, you try to find the scaffolds, the relevant scaffolds in the patent corpus that are linked to your query target. And of course, with this being the Open PHACTS API, you can very quickly connect to other sources of information. So for compounds or targets, you can quickly access pharmacology data from ChEMBL, or pathway information from wiki pathways. In terms of availability, the API calls that are related to patents will be released to production very soon, and when that happens, you can contact me, and I would be very happy to send you the 9 workflows that I used during this webinar. In terms of licensing, the annotations from SureChEMBL, so that's the chemistry annotations, are licensed under CC BY SA, which is the normal EBI license, and the SciByte annotations, these are the gene and disease annotations, are licensed under a non-commercial license. Finally, if you would like to find out more about SureChEMBL, what it does, and some applications, you can check out these 3 publications that we published recently. When it comes to the Open PHACTS API and the questions and the use cases that you could answer using the API, these are 2 very nice publications. And finally, I would like to thank very much my colleagues in the ChEMBL and SureChEMBL groups, and also the people from the Open PHACTS Consortium, which integrated our data and make the data available via the API. Of course, all our funders and funding agencies, our technology vendors and partners, without which SureChEMBL wouldn't have been possible. And of course, all of you for listening, and I will be happy to take any questions that you may have.
Thank you, George, for that great talk. And what we'll do now is, as people think of extra questions, we're just going to unmute those of you that have asked questions already. And first, I know there's already a couple of questions in the backlog. So first of all, I'll just unmute John Pan, who I think had a question about the sort of the coverage of SureChEMBL. Can you hear us, John? John? Okay, let me just ask his question on his behalf, and hopefully he can hear us okay. And by all means, jump in. So John asks, does SureChEMBL pipeline, entity recognition pipeline, recognize biologics or other small molecule drugs? Can it find sequences for antibody-based biologics?
Okay, so the entity extractor can find mentions of trivial names and IUPAC names. And of course, we have also the tool that will find the images and converts them to structures. So the answer is no, it cannot deal with sequences or biologics unless they are reported in the form of an IUPAC name or a trivial name.
Okay. Well, there's actually quite a few questions, so I know we'll try and get through the ones that have already been asked, and then if people have got follow-up questions, we'll try and cover that, and we'll equally happy to answer questions later on by Twitter or through email. Let me just move to Ian Harrow's question, so I'll read it out and just check I've understood it. So Ian asks, what are the error rates like for the automated recognition of chemistry text and structure entities?
Yes. So for that, we published a paper very recently, last summer, which tried to compare the entities, the chemistry entities from SureChEMBL to the chemistry entities that come from manually curated sources like SciFinder, for example. And what we found, although there is a slightly, the scope between the 2 sources and resources is slightly different, what we found is that there is an overlap in the terms of chemistry between 65 to 70% when it comes to coverage of chemistry from different patents. Of course, having said that, there is this is a fully automated and high throughput approach, so there will be errors, and most of the errors are associated with OCR, so with the scanning of the patents that are not electronic and converting them to digital text. then this introduces usually spurious characters which make the recognition of entities more difficult and introduces false negatives. So this is the main source of errors.
Great, thanks George. The next question is from a C merchant, and they ask, what is the performance of the SureChEMBL pipeline in terms of proportion of true positives identified and the proportion of false positives generated?
Again, this is related to the previous question, I think, in terms of fidelity or accuracy and precision. So again, the same answer, I guess similar answer applies. There's a publication with GSK last year in terms of chemistry coverage. What I will say also is that there's a lack of manually annotated corpora of patent documents, so the comparison, systematic comparison in terms of chemistry and biology is difficult because of that. But if people had ideas and they had their own data set and they would like to use it to compare SureChEMBL with other sources, we will be happy to help, so they can get in touch and we can help them do this kind of comparison.
Great, thank you. Then the next one was from Mark Forster, and Mark asks how easy or difficult it would be to train and search the system using terms relevant to agrochemical research as opposed to human pharmacology.
It wouldn't be very difficult. We would just have to augment the dictionaries, for example, that we have with the new related and relevant gene and disease entities. So it would be straightforward, I would say.
Okay. And then I think Jenny Vikland asks perhaps a general question which I can probably help answer because it was something I may have missed at the beginning. So just a recap of where we are with the Open PHACTS deliverables. So George mentioned that the work he showed was using our development platform that we've been testing with our sort of members over the last few months. And what's been generated so far is the patent corpus in SureChEMBL up to April 2015. And then our next update will then include the last year's patents up to end of March 2016. And we hope to have that ready in early May because we've got to process it and then add it to the platform. And our goal for releasing these calls into production to the wider community is in April, so a few weeks away, but we're busy doing the testing at the moment. So that's where we are with the sort of release schedule, and then we'll be doing quarterly updates probably on the patent corpuses coming into Open PHACTS to start with, and then see how that goes based on your feedback and the wider community. So I hope that helps, Jenny, with that question. And then perhaps as we come toward just one couple of more questions to take off the list. So Adam Carter asks us, are you using some workflow pipeline management system to link together the stages of the analysis that you're running on AWS? So quite a technical.
Okay, yes, we use the native SQS system in AWS. So that's a queuing system that enables the communication between the different components that we have in that pipeline that I showed you. So SQS by AWS. It's a queuing system.
Okay, thanks. Let's just see if any other questions are coming into the desk, and I equally want to make sure that people can get off to their next meeting too. So just as we wait to see, maybe what we'll do is if there's any other questions that we've missed or you want to ask, by all means get in touch with us through the channels that we mentioned, so info@openphacsfoundation.org or through our Twitter account or looking at our website.
People could also, excuse me to interrupt, Nick, people could also send me, if it's a question related to SureChEMBL or the annotations, they could also send an email to my email address, which is on the slide.
Yes, and that's a great point, and equally want to thank George for a great talk. It was really well received in Vienna, and I hope everyone today enjoyed it too. I mean, I think there's a tremendous amount of work gone in both to linking SureChEMBL with Open PHACTS and equally this early work around exploring question-driven pipelines or workflows that George has talked about today. So many thanks to you, George, for that. Just as we sort of complete today's talk and updates, just a note that these are sort of a start of a series of webinars on what people are using Open PHACTS for. So our next webinar will be in about 4 weeks' time at the end of April, and this one is on target validation with Open PHACTS, and a number of our sort of pharma customers and users will be talking about how they're using Open PHACTS for target validation, and we'll equally announce talks for May and June in the coming weeks as well. And as I say, if people have any other questions on Open PHACTS, please get in contact. And it just leaves me to thank you for your attention today, for the questions that people have asked, and once again thank George for a great talk, and wish you a good rest of the week. Goodbye.